which is the League of European Accelerator-Based Photon Sources, which is a collaborative consortium coordinated to transform the European photon sources towards the next generation of facilities. She was working at CERN for 3 years, from 82 to 85, and then a long time in the Laboratorio Nazionale dei Frascati, all'INFN, from 1985 to 2012, when she moved to ALBA. Just to mention that she is a member of many committees, like chair of the European Physical Society for Accelerator Group, member of the EPS Executive Committee, and she has been member of advisory committees for CERN, for PSI, XFEL, and many other machines, which I cannot even pronounce. So she has been in many, many committees. She's fellow of the European Physical Society, and she has also been awarded in 2013 by el Presidente de la Repubblica Italiana with the honor ufficiale dell'Ordine della Stella d'Italia, which is probably a big honor. So it is, of course, a big honor for us to have you here. So thank you very much for accepting the invitation, and enjoy the talk.
Okay, now it works. Thank you for the presentation, but especially for the invitation. As I was saying to Bruno, to your director, just a few minutes ago, I've been here in Barcelona working for now it's 7 years. Then it starts, now it's on, but then at a certain point, okay, I'll try not to touch it. And this is the first time I come to the Universidad de Barcelona, the Facultad de Física de la Universidad de Barcelona. And so I'm very happy to be here and to be able to okay. Yes. To show you what is ALBA and what we are doing. And for that I start from a picture that I wanted to put here, not only because we are at the eCube, but because it shows also synchrotron light. As you will know, this is the image of the Via Láctea, and there are the light of stars. And if you have seen one of the latest news, one of the few scientific news that appears in the media, but this was just a few days ago, from El País, detectada una extraña emisión de radio entre dos cúmulos de galaxias. And it says the phenomenon observed is the synchrotron radiation, because synchrotron radiation is nothing else than the radiation emitted by particles, charged particles, accelerated, and with a transverse acceleration, which means they are emitting radiation. And this is what is the synchrotron radiation. But of course, one thing is what happens in the universe. Another thing is to use that to make it usable and useful in our labs. And this is what a synchrotron does. The name synchrotron is the name of an accelerator. An accelerator, which usually is a circular accelerator, where particles, charged particles, travel in trajectories, and they are used. Synchrotrons are used for producing the light, but also for collisions. In fact, when you presented me as the only woman director of synchrotron, we are talking of this kind of synchrotron that we are seeing today. But LHC is also a synchrotron, if we speak as an accelerator. And there we have another woman who is the director. So what we do to produce this synchrotron radiation in our labs, we have to accelerate particles to a certain energy. So we have to give energy to particles, and we need magnetic fields to guide the trajectories of the particles inside the accelerators. And these are the particle accelerators. Particle accelerators, as you will know, are used for producing beams of a certain energy, of a certain dimension, of a certain current with charged particles. So they are used for electrons or positrons, they are used for protons, antiprotons, they are used for ions. And the principles of accelerators are, of course, the same, whether you use them for doing the 30 kilometers LHC, whether you do it for the 300 meters of ALBA. And the bricks are magnetic fields and electric fields. Of course, the technology needed for producing the magnetic field of the electric field changes with the kind of particle and mainly with the need of the energy of the particle. Higher energy means you need much powerful magnetic fields and electric fields. And in our accelerators, our magnetic fields are done through what we are called the magnets, which are different kind of magnets, and that in the case of ALBA are just normal conducting magnet, electromagnets, while in the case of LHC, we need superconducting magnets because the energy is of course much higher. And the LHC in particular is the 27 kilometer circumference accelerator under the area of Geneva and nearby France. And it's used just for fundamental science. This is the main difference. Many times I'm asked, what is the difference between CERN and ALBA? Apart from the size, and therefore the cost, the main difference is that at CERN, the science is fundamental science, to answer fundamental questions. But while at ALBA, the science is much more applied. But the technological advances that are needed to do this is what is used for producing a huge amount of particle accelerators, which are useful for the society. And just to mention, this is a picture of a part of a picture, and then a design of what are the magnets at LHC, and what are the detectors at LHC, which are a big cathedral of technology, which are used to see the collisions in the interaction point of LHC. And as I said before, this fundamental science means that we need technological development, which then go to applied science, training and education, answer to societal challenge, innovation, collaboration, open science, and social awareness. So this is the starting point, the fundamental science. But then the number of accelerators in the world is thousands of accelerators. And those which are famous, those with the accelerator with a name, like LHC, ALBA, are very few, are just a very small percentage of the total amount of accelerators which are used for industrial usage, for medical applications, for isotope production. So, and these come from the steps that are done during the construction of the next accelerator for high energy physics, or for getting more photons on a sample, as we do in ALBA. And before starting to talk about ALBA, I wanted to show you one of the possibilities of the accelerator are the synchrotrons for protons and carbon ions, which can be used for hadron therapy. The hadron therapy is a technique which is an evolution of what is the radiotherapy that we all know, that is more advanced in the sense that while we use radiotherapy, the photons start to kill cells or to damage the cells already from the very beginning until they reach the tumor, while protons or carbon ions, which are accelerated through these synchrotrons for hadron therapy, they deliver the maximum energy only at a certain depth, so that the damage done to the healthy tissues around the tumor is much less. And this is a technique that is increasing in the world, and probably there will be some also here in Barcelona in the next future. There is no one in Spain. They are now building one in Madrid for protons with a smaller kind of accelerator, but for carbon ions you need the synchrotron. So this is one of the evolution of what comes from CERN and the other laboratories. Then let's go now to synchrotrons for synchrotron light production. This map shows the number of synchrotrons that are around the world, similar to ALBA, most of them much older than ALBA, but as you can see, the yellow names correspond to synchrotrons which are being built nowadays. So it's a field which is in evolution, and which increases because the demand of the usage of such instruments for science is always increasing. Of course, they are very much on the northern part of the world, but there is one in Africa, in Australia, there is one in Brazil, and they are building the new one, and they start to talk of having a synchrotron for Africa, an African light source. ALBA is the Spanish synchrotron, is in Cerdanyola del Vallès. I hope you have visited. How many people have visited from here? Okay, so it's some 20% maybe, and we are in a so this fact that today I'm here, I'm even more happy that at least most of you, I hope, that will come also to visit ALBA, and at least you will know what we are doing there. It took me today, I think, 25 minutes by taxi so we are really very near. We are near the UAB. ALBA, this is in Spanish, is a story of success in the science panorama of Spain. It's a public institution, and it's funded 50% by the central government, today the Ministerio de Ciencia, Innovación y Universidades, and 50% by the Generalitat, today by the Departament de Empresa y Conocimiento. We are national from the point of view of the funding, but we are international in our staff, in our users, and in our collaboration. So it's a national infrastructure, one of the biggest, I would say the biggest in Spain. We can compare with the ESC in Canarias, but it's the biggest initial funding for a scientific infrastructure in Spain. So how do we produce this synchrotron light? Of course, as I said, we need the particles, we need the magnetic fields, we need the electric fields which are produced in radio frequency cavity. And the magnetic field guide the trajectory. Every time that the beam of particles is bent, it produces radiation. It produces radiation whose characteristics depends on the energy of the particle, and of course on the bending radius, therefore on the magnetic field. And what kind of radiation we can produce? We can produce in this accelerator-based photon sources, we go from the range of the terahertz up to the hard X-ray. So we are able to produce X-rays up to 80, 100 keV. If I talk of all the synchrotrons in the world, in ALBA we reach something like 60 keV. And therefore with a strong, powerful capacity of interacting with matter and of giving information at the level of course, molecular level and up to the atomic level for some of the techniques. The light is emitted by the in all the magnets, dipoles, which bend the trajectory and make the particles go around in a circle. So every time they pass through a dipole, they emit a cone of light. But in between, we use what we call insertion devices, which are magnetic fields with different sign, so that the particle inside wiggles and produce cones of light where we can tune also the energy of the photon. Here we cannot tune the energy of the photon because these are fixed magnetic fields to keep the particles going on, while here we have a huge range of tunability of the photon energy and of the photon flux. And there are two different kinds of insertion device, those which are with a longer period in which the emission in each of the wiggler adds incoherently, and those with smaller period where you get more coherent light. So the light which we get has high brilliance and flux, has wavelength tunability, polarization. You can modify the field, the direction of the magnetic field. You can change the polarization. It has time structure, and it's a collimated coherent radiation. So it's a powerful tool for probing the matter. As an example, I put here the spectral flux of the ALBA photon sources, where you see there are some which are continuous. It's like a black body radiation, and these are those corresponding to the dipoles. Then we have those continuous which correspond to the wiggler, and when the wiggling period is very small, then instead of having a continuous spectra, you have harmonics. And you increase also the spectral flux. And so it covers different necessities from the experimental point of view. The structure of a synchrotron is the accelerator, which is round. You obtain the electrons that are to be accelerated, obtained by in the case of ALBA, from what we call the gun of electrons. Is essentially a tungsten wire which we heat at to 1500 K, so that it emits electron, and then we put electric fields, radio frequency electric fields that give the first energy. We reach 100 MeV in the first part of the acceleration, which is a linear part. Then it goes inside a booster, which is in the inner part of the tunnel, where it gets up to 3 GeV, and then it is injected in the external synchrotron, where it keeps going on for days and nights. And around the synchrotron, there are the windows from which the light is extracted, and each photon beam goes up to what we call beamline, experimental beamline. Each beamline specialized on a different technique, and each beamline having the photon flux that we saw before, which are different. The history of ALBA started, I have here a date, which is 2003. In fact, the history of ALBA started before that, because to get the approval of such a project, it took almost 1 decade, in which a group of people led by Ramon Pascual, that maybe many of you know, and together with others like the previous director, Joan Bordas, or Salvador Ferrer, who studied here, I think, when he was young. They worked for the preparation of such a project, and from the point of view also of convincing the politicians at that time that it was a good investment to be done. It took time, but in 2003 the project was approved, and not only approved, but it was assured the funding of the project up to now and even further. So this was a very wise decision. Of course, in that moment, Spain was living a good economical situation, and that, of course, helped. But the fact that the funding was assured along for the future has allowed us not only to construct, to put in operation, but also to start the full production and to increase the number of beamlines. The number of beamlines is an important part of the facility, of course, because electrons go around and they emit synchrotron light around the whole circumference, and it's good to have as many ports as possible. The project started with 7 beamlines. From 2014, we have started 1 beamline per year. From the point where you start a beamline to the point where the users come, it may go from 4 to 6 years, depending on the complexity of the beamline. So in this moment, we have 8 beamlines in operation and 4 more in construction, and we are planning the new ones. I showed you before the tunnel of LEC, and this is the tunnel of ALBA. You see that it's different because it looks more complex. There we have only the big cryostat for the superconducting magnets. Here we have normal conducting magnets. This is the booster, and this is the synchrotron. Here we have the cavity which gives the energy to the electrons. The electrons, every time they emit photons, of course, they lose energy, and this small amount of energy must be recuperated after one turn. And this is one image of the tunnel where the electrons run at 3 GeV, which means, of course, they are at the velocity of light, doing 1 million turns per second in the synchrotron. Now, what we use, why we have the different techniques? Well, this is a slide I use for other kind of public, not for you who are physicists, but just to say that the fact that there are different techniques is because we use ALBA for studying the different kind of interaction of the light with the matter. And therefore, we have beamlines which use fluorescence, others which use the transmission, others which use the scattering, which use the photoemission, that which use the diffraction. So each beamline is specialized, and as today, we have 8 beamlines which cover from the infrared up to tens of keV. 4 of them are more dedicated to material science, and 4 of them more dedicated to life science. Even if in many of them we can do experiments from both fields. One is one dedicated to powder diffraction with high pressure and high resolution station. In fact, we have 8 beamlines, but some of them have 2 end stations, so we have up to 12 different instruments, of which 8 can work at the same time. We have a beamline for photoemission with one of the end stations dedicated to near ambient pressure photoemission. We have one for absorption and emission spectroscopy. We have one dedicated to magnetic materials, is for resonant absorption and scattering. Then we have one non-crystalline diffraction where you can do small angle scattering, wide angle scattering, also GSACs. We have one for macromolecular crystallography, one for cryo-nanotomography, a transmission microscopy, and one for infrared. And all of these beamlines are high-tech beamlines, and some of them were, you have seen the number of synchrotrons in the world. Of course, there are some of the beamlines that are everywhere in all synchrotrons. For example, all synchrotrons have a macromolecular crystallography or a powder diffraction. But there are some of them, as this cryo-nanotomography, which were quite special when they were done. And in this moment in the world, there are only 3 of them, and we are the reference for this kind of technology. And also the Boreas, for example, the second station in this moment is unique in the world. So this was a wise decision because it could give, when ALBA started the operation, there was already a community of about few hundred, 200 researchers in Spain who had at that point the technologies they knew in their synchrotron. But then there were also new instruments that with no community behind, but that are now those who have who are specific of ALBA, give us more visibility also around the world. We are building for beamlines. You can see there are different stages of construction. This is the Lorea, which is an angle resolved photoemission, will be the next one to come. Notos, also we are building the hatch, and we have some part of the beamline already at ALBA. A new microfocus macromolecular crystallography with a smaller beam, dedicated to smaller crystals, and one hard disk ray imaging, which will complement the one we have for with soft disk ray imaging. It's very important when we talk of a synchrotron. It's a facility for users. The users come to ALBA all the year around, and it's very important what the service you give to the users and the availability of the photons when they arrive there. They have, for example, there are users, the average time for an experiment is of the order of 3 days. Of course, the users come from wherever in the world, and they come to ALBA and they need the photons working. So one important point is how much of the almost 6,000 hours per year that we promise when we define our calendar are given really to the users. And we are at a number which is over 98%. And this is, if we compare with those synchrotrons which are around the world, it's very competitive. We are among the best. And I say that because this is not an easy performance indicator to reach, especially when you are in a facility which has been done in a place where there was no experience at all about building a large infrastructure based on an accelerator. And since I came after this was done, I can say that very loud, that it was an excellent work from the very beginning. Because to go there, you have to have thousands of systems that work perfectly and work always. So you need to have thought, design them, build them, put in operation, maintain them at the highest level. And this is what ALBA is doing today. So what we do, I have few examples. From the beginning, we have been doing hundreds of experiments. So I will not, it's impossible to talk about all of them, so I took some of the examples. This is an image of a cell. Here you have the membrane of the nucleus of the cells. This is a cell which has amyotrophic lateral sclerosis. And we can see the cell with a resolution of the order of 30 nanometers, but we can see it in 3D. We don't need to slice the cells as it is done in the cryo-electron microscope, which can reach a better resolution of the order of 10 nanometers. But here we keep the cell as a whole, and so we see really in 3D the full cell. So this is a technique which is essential for many of the investigations that are done in life science. We resolve protein structure. This is done in Shalok. We have hundreds of proteins structure resolved. And here we can see the position of the hundreds of thousands of atoms of a structure with resolution at the atomic scale. We do that to understand diseases. Another example of a cell infected by the parasite of malaria. This is an example which is an investigation done by together with the Grenoble synchrotron at SRF, where they have some technique on X-ray fluorescence microscope that we still don't have, but together with our beamline in Mistral. And of course, it's very useful to design new drugs. In the Shalok beamline, this one for macromolecular crystallography, we have not only researchers from the public institution, but also industrial users who come on pharma users. And it's very important to see the effect of the drugs directly on the structure of the cell. We work on energy materials. Several experiments are done on optimizing materials for batteries. For example, not only for lithium batteries, but also for those batteries which are based on different elements, like this one, which is done with sodium, because lithium is scarce and is expensive, and there are groups around the world working on developing batteries based on more easy to find elements, like, for example, sodium or even calcium. We advance in nanotechnology. Here you see an image of skyrmions, these magnetic vortices at the level of nanometers, and it's very important to use this for, of course, for data transmission or for future computers. We investigate nanomagnetism. Here you have an holograph, magnetic hologram done at the Boreas station, the one that I say is quite unique in the world. And of course, this is very important for spintronic applications. We have a strong involvement in the studies of new catalysis, together with very strong groups that are in Spain, for example, in Valencia. We work also on food, the production and conservation, both to make even better the food that we all eat, and in the rich part of the world. For example, there is a company from Barcelona who is doing chocolate, and they come to ALBA to understand how to better produce their chocolate, their products, considering the difference in the production system. But what is more important than that, which is nice to see and to say, but it's more important that we work also on the food for those regions of the world where the alimentation is a problem. For example, how to improve the amount of selenium inside the wheat plants, which is very, very important. And we work also in the cultural heritage. As an example, I put here the chapel of San Miguel de Pedralbes, which was recently renovated. It has been opened, I think, 1 year ago to the public, where there were some black spots, not easy to understand what they were, and they took a small sample of this spot and was analyzed in ALBA, and we saw that it was a kind of fungi, and so that they could treat it. And I'm very happy that we participated also in the renovation of such a beautiful part of our cultural heritage. So we help solving all the grand challenges of society in health, energy, environment, food, heritage, and fundamental science. Our users, here you see the history from 2011. I said we started operation in 2012, but in 2011 some users were already using and helping also in commissioning the beam line, so they were already working with ALBA. But you can see the number of users is increasing, and is still increasing also because we optimize the usage of the instrument in order to be able to do experiments always in a shorter time, and to have more users, because there is a long list of users who cannot enter because of the time that is available. We have done more than 1,500 experiments so far. And of course, this reflects in scientific productivity, number of papers, a number of papers with high impact factor, which is increasing. The one performance indicator of the synchrotrons is how many publications with impact factor larger than 7, which is the percentage. The best are around 20%. If we are above this 20%, of the order of 30%. And we have collaboration users from all over Spain. Here are few of them. Of course, all the universities are also our users. And also from the rest of the world. With the registered institution in our database is keeping increasing, especially those from the rest of the world. I think from Spain it will be not easy to increase the number of registered institutions because almost all scientific institutions are now in our database. ALBA is used more or less 2/3 by national users and 1/3 by international users. Here is the distribution of the national users in the Comunidad Autónoma. Of course, Catalonia is the one which is using us the most, not only because of the vicinity, but also because of the number of institutions that Catalonia has. Then comes Madrid, Valencia, País Vasco, and so on. And the international users of ALBA, you can see here the number of proposals from ALBA submitted and approved is 1,700 and 1,000 approved. From the international, about 1,000, half of them have been approved. And we have had proposals from 41 countries. You can see here the distribution. Those who are using us more are Germany, France, Italy, and UK. We are not only dedicated to the academic and the public research, but also to the industrial research and to innovation. So we have users who come from the industry, and the distribution of the fields is dominated by pharma and nanotechnology. But it's not only the usage of our beamlines, but also the innovation and the technology transfers due to the development of technology that are done in ALBA. So to have ALBA, to build and to develop ALBA, we develop technology. We have a group of engineers, for example, who are always doing new designs. These innovative designs go to the industry, and then the industry can work and can develop their own designs and be competitive in the international world of scientific infrastructures. Our access modes are two. One is the public access mode, which is free and is based on competitive access. And of course, the calls, we have 2 calls per year. The next one will be open in a few weeks from now. And is based on excellence. We have international evaluation panel, which takes all the proposals that reach ALBA, and they give a list of priority based just on excellence. And of course, the access is free, but and then the results are public. And there is another access mode which is private, and this is a direct access, and is based on technical feasibility, and this access must cover the cost of the service, but the results can be private and confidential. This is very important for the industry, because the industry sometimes we can say they are using our beamlines. For example, one of our biggest users is Henkel, this multinational who work on chemistry, adhesive, and so on. And is if you see here the number of companies, this one is Henkel. But of course, not all the results they get are public. They want to maintain the confidentiality. But it's very important that we show to the industry that they have in us instrument that they can use to complement what they have in their own laboratories. It's very important for us the commitment in training. In training at all levels, we have students from the formación professional dual, about 15 students per year. I have not said before, but we are at ALBA, we are around 220 people in ALBA, plus the students. And of course, we keep the number of students at the level that we can tutor them and we can dedicate one person to each student. So we have formación profesional, undergraduate, and of course, PhD students working directly at ALBA with a special doing their thesis working at ALBA. But of course, there are many others who come through the competitive calls. We have very often PhD students working at our beamlines through the proposals their group are granted in our beamlines. The PhD program is our students work on material science, life science, accelerator physics, engineering, and data science. So there is a long list of possibilities for working as a PhD student in ALBA. What is important is to have collaboration with an external institute. In every of our beamlines, we have a dedicated team of scientists who work for that beamline, who give service to the users, but who do their own research. So our PhD students are students who work in a project which is partly done in ALBA with a tutor in ALBA, but partly done in another institution outside, which can be a university or can be a research institution, and can be from Spain or can be also from abroad. For example, we have some who come from Germany, from some of the Max Planck institutes. Another important part is the communication to the society of the science. We have a long list of visits along the year. We try to put the visit of the schools, for example, in those weeks in which we are not working for users, so that they can walk around without making too much noise when the users are working. But on top of that, we have visit of institutions, of universities, and I invite you, if you are interested, to go to the webpage of ALBA and see how you can visit us. We have 1 day per year. We do an open day. The next will be on 29th of June. I don't invite you there because we don't have any more space. But if you are interested, just send an email and put on the list for the next one, because we keep the number of assistants in 1 day at about 2,000 and something. We cannot open to 10,000 people because of problems in the organization. So this is for us very important, the possibility of showing to the society what we do, why we do it, and how much important is for the society to have scientific infrastructures. And we want to attract people, young children, girls, to science. But it's not only for those who will be doing science when they grow up. It's also important for those who will be lawyers or who will be politicians, mainly politicians. That would be good that they remember, when I was a child, I went there and I liked that, so maybe it's useful. And one thing that we have done, and I'm very happy of this project, is what we call Mission ALBA. It's a project for children of 9-11 years for the whole Spain. It's a project done all on internet, so that it reaches all those schools that cannot come too easily to visit ALBA. Because of course we get visits from schools, but they are mostly from around us. And we never got a visit from Extremadura. And in this way, we reached more than 7,000 students, and we are aiming for next year to increase that number. We started with a small number, also to get the feeling how was the response. The response was excellent. We got response from the whole community of Spain. I think only Ceuta didn't send any school. And there is one prize, and it was the prize was given to a school in the village of Guadalupe in Extremadura. So the prize is that some of our scientists go there and spend one day with the children. Of course, we are in a net of collaboration on photon science with other countries, for example, Portugal, Mexico. Sesame is a synchrotron which is in Jordan, and it's a synchrotron which is a symbol of what science can do for the society and for peace. It's a synchrotron with is smaller than ALBA, and the history has been much longer, but yesterday they got the first publication, the first paper with data taken at Sesame. Sesame is near Amman, but the owners of Sesame are Jordan, are Iran, Israel, Palestine, Turkey, Chypre. So it's a place where science is done for peace, and it's very important. And we are collaborating very much with Sesame. And as I said before, there is also a future project of African resource where we are also working with that. And beyond photon science, we are also working with other facilities, mainly with CERN, also for the future. You may know that this year there is the process for defining what will be the European strategy for particle physics in the next 7 years. We are working there also inside the group of the preparatory group for this strategy, and we are working especially for the future accelerators. The FCC is the Future Circular Collider project. Is a design, and is an accelerator that in principle should be 100 kilometers long. And of course, we work in the net of synchrotron users in Europe. There are more than 30,000 users in Europe. They visit. This is here we have synchrotrons, and here we have countries. And you see that there is a long, a strong communication among the countries and the different facilities. And so we are using a new consortium, which is called LIPS. It's a consortium with all the synchrotrons and FELs that are in Europe. So the APS means accelerator-based photon source. And here you have the list of facilities. And we're working there because we want to have a single voice in Europe, mainly towards the European Commission, but also towards our national funding agencies, to show that we can work together, we can develop together technologies that are useful for increasing the capabilities of the photon sources and increasing the capabilities of our instruments for the research environment in Europe. And not only for the research, but mainly also for the industry. We want to develop techniques and to share this development with industrial partners in Europe in order to have a strong voice and strong capabilities of Europe as a whole in the general panorama where China and US are developing so quickly, especially China, and we want to put together all our capacities to be stronger as Europeans. And another thing that I want to mention finally is that we are a photon source, but of course there are techniques which are complementary or synergetic with what we do at ALBA. And so we are opening to possibilities of increasing the number of instruments based on other technology. And we are in a consortium also of different institutions in Catalonia. I have not put the names because we have just presented the proposal to the FEDER funds of the Generalitat, and so until we don't have the okay that I hope we will have, I don't put the names here, but we are aiming at being part of an advanced microscope platform in Catalonia, of which the UBI is also one of the partners of this platform. There will be some of the microscope that will be in the UB and others that will be in ALBA, and we are working together to sum up also here our efforts. And the long-term future is that, as I said before, we are now building for beamlines. We aim to build more beamlines, and after 10 years from now, we are starting to think how to upgrade the whole accelerator to make the photon beam more coherent and more bright. This means changing the whole structure of the accelerator is a big upgrade, and we are starting to work also on that, on the design of this upgrade. And so this is the end, and I want to summarize what we are. We are mainly a research infrastructure. We are working, one of our mission is the innovation, the training, and the outreach. And thanks for your attention.
Okay, thank you very much for this very comprehensive presentation of the synchrotron activities. So now we have some time to ask questions or comments.
Currently, can you give an idea of what is the fraction of the time that is used of ALBA for private self-funded time and what is used in public?
Yes, I have the exact number if you want, but it's a low number. The private usage is very low. Last year it was 1.5%. But what I have to say is that we have to compare what the others do. Other synchrotrons, for example, one of the synchrotron which has a highest usage from the industrial community is Diamond in UK, which is running since almost 8 years more than ALBA, and they have 3%. In a country where, of course, the industry is strong, and especially they know what to do with a synchrotron, and we started from zero. And we are. It's very important. We do the outreach to the industrial community. Just a few days ago, we had a meeting at ALBA dedicated to polymers, and we invited all the industry. We have, of course, nets of names and contacts for industries also through through the Generalitat and through the government of Spain. And we invited, and they were more than were about 70 people, which is very is a number which is high with respect to what happens in other synchrotrons. So it's a number that is increasing. We started in 2013 with just 0.2%, and now we are 1.5%, and it's increasing. But it's very important. This is one thing, but there is another thing, is that in those who come through the public access, we always ask to the PIs to specify if what they are doing is somehow related to industrial applications, or if there are also industries working together. And in that case, we have that from the total amount, we have 25% who are working also with industry. So if you want, this is a number which better represents how much a synchrotron is useful for the industry. If they come through the competitive access, they have to publish the results. This is the difference, and they don't pay anything.
Any other questions or comments?
You have just quickly mentioned it, but you're already thinking in ALBA 2. Can you quickly describe what it would be? New building or reusing the same building, changing the...
No,
and who will pay for it?
yes. Well, who will pay? We have only our administrations who have to pay for that. Yeah, so one should that's also why we have started now, because it takes time to design, but it takes more time to convince someone to pay. What we are aiming is what they are already doing in some of the synchrotrons. For example, ESRF. ESRF, you may know that this year is shut down and will be also shut down almost the whole 2020, because they are doing this upgrade, which means changing the whole structure of the accelerator. Not the building, not the injector, not the beamline. The beamline maybe they must have some adjustment. But the idea is to change the accelerator. And the idea is very simple. You have seen, to produce the light, we use dipoles. And in these dipoles, the light is emitted. The size of the electron beam, of course, define also which is the size of the photon beam. The smallest the size of the electron beam, the more focused and the more coherent, especially, is the photon beam. If you increase the number of dipoles and you make this emission more concentrated, you can get smaller emittances, smaller size of the electron beam. So what you do is to substitute a ring where now we have 32 dipoles around the ring. It should go to 3 times as much, but smaller. This will make the beam smaller. So this is the principle. It looks very simple. Of course, it means that you have to change the whole accelerator, the vacuum chamber, all the other magnets around the dipoles. It may cost some tens of millions. And then if you include that when you do that, you want also to upgrade the beam lines, because if you make more focused photon beam, you will need to change the detectors on the optics. It can go up to 100 millions easily. And why it is done now and not before? Because to go to this technique where you have to decrease the beam, the electron beam, which means increasing the difficulties in terms of stability of small magnets or vacuum chamber. There is a number of technological improvements that have been done in the last few years that were not available when ALBA was done, or were the oldest, or this third synchrotron. ALBA is a third synchrotron, third generation synchrotron radiation, and now these new ones are what we call the fourth generation. And there is only one working in Sweden, and they were the ones who started this kind of new technique. They made a full new synchrotron, which is working since 2 years ago.
Hi. Are there any special calls for PhD grants, or is there any public call where people can apply for that? And
for PhD, we are not doing this kind of call. We are doing this kind of call for undergraduate and for FP. There we do a call, and then the students can apply. PhD, as I said before, every PhD we have comes through a collaboration. So what we want to do is to increase this number of collaborations with special institutions, with those who are the most expert of our users, and that we can develop together, projects together. And these are, so it comes not through an open call. Up to now, it has not gone like that. We are discussing also on how to improve and to increase the number of students. But up to now we have, as I said, around 15 students, because in principle we have one student, maximum 2 per beamline, if there are 2 different instruments. And then we have also students, for example, in the accelerator division to work on accelerators for these new projects of with CERN, but always through collaborating project. And we also, what we do also is to participate to the national program, los proyectos nacionales, and there sometimes we can apply, and we have the possibility of having some students, but we don't have open calls.
Just one question following the upgrade you were mentioning, because the final aim to reduce the beam spot of the accelerator is to increase
to increase the brightness, the number of photons, and to increase the coherence. Of course, we have is not only the number of photons per that you get on the sample, but also the coherence of these photons, and it's an evolution which is. Which goes in the sense that have gone the FELs. No? The FELs are photon beams which are not only with better time resolution, because they have shorter pulses, but they have much more coherence than what we have in synchrotrons. And so this is the idea is to go to a better coherence of the photon beams. And of course, with a better coherence, you can get better probing characteristics in many of the techniques. I say in many of the techniques. It doesn't mean that all of them will benefit. There are some techniques that will not, in principle, be specially benefited by this upgrade. So, so what we are also looking at is, should we go in that direction, or should we choose some other direction? Because all these techniques that we are looking at, I would say half of them have a clear advantage, but the others not. And then also inside the LEAPS, what we want to discuss is especially this. Where should the whole diversity of synchrotrons go? Should we aim at having this 4th generation everywhere, or there are techniques that they better have a larger beam? In some of the techniques, they do a very small focus beam, and then they put something to make it blow. And then we are discussing also this.
A few years ago, it seemed that coherence was the new generation of synchrotrons, no? Like
Yes.
LCLS at a slag and so on and so forth. And maybe this is kind of,
Yes,
as you said,
yes.
being rethought now.
Yes.
Any other questions? I wanted to ask us a very short question. Is in the market, let's say, of synchrotrons, is there something singular about ALBA? I mean, when someone is going to decide where to apply, do they have some special reason to apply to your synchrotron, apart from this 98% time that is working, which is extremely important, but is there any other?
Yes. This is important, of course. This number says that if you have a user, and then they will come back. But as I said before, there are some of the techniques that are really special at ALBA. For example, this technique of the cryo transmission microscope. This is really, we are the best. And a few days ago, there was a beamline responsible from Soleil, she was here measuring at us because they don't have this kind of technique. Or the one of Boreas also is specific, and there are no other in the world in this moment. Of course, as you have seen, we have what we call an overbooking factor of around 1.8. It means that half of the proposals we receive are not granted beam time. Then what most users do if they have this problem is to apply to several synchrotrons also, of course. And then and this is done by Spanish users who go to other synchrotrons. But it's very important the quality of the beam line, the support you get from the people also. Of course, Barcelona has something more than many other places. To come to Barcelona is something that everybody likes. So this is also something that is very useful, because if a user has to decide, should I go to Hamburg or to Barcelona? Well, let's see what they have in Barcelona, and I will go there if it fits my needs. So it's a combination of things. But the most important, I would say, is the quality of the stations. And one important thing that will become more important in the future is what you do with the data. Synchrotrons are going from facilities which provide photons to facilities which provide data, and which provide data with not data on a pen drive or on a disk, useful data, already pre-analyzed. And this is something that is, I didn't mention, but is one of the development that also will be done also in collaboration with LIPS, is what we call data analytics. We need not only the number, the amount of data, the size of the data will increase, because of course our detectors are always quicker and they get more data, is the science of data and the usefulness of certain data. And it will be very important that if a user is making an experiment, to have a first analysis and see if the experiment must be changed, if the sample is okay or not, and that you should do online. And this is an evolution that all the synchrotrons are facing.
Okay, so if there are no more questions, before closing, just remind you that Professor Biscari will meet with students of ICUB at 2:30 in the common blue room in the 7th floor. So without any further things, let's thank the speaker again, and thank you everyone.